this video, we're going to continue our discussion on things that can complicate drug elimination kinetics by discussing the effect of urine pH on drug elimination. To understand how this works, it's important to understand how pH affects the chemical structure of drugs. Many drugs contain ionizable groups, which means they can either accept or lose a proton to become charged. Basic ionizable groups can gain a proton in order to become charged. So for example, basic amine groups in their uncharged state have the formula NH2, but in an acidic enough environment, they can become protonated to have the formula NH3 with a positive charge. Acidic ionizable groups lose a proton in order to become charged. So for example, acidic carboxylic acids have the formula COOH when they are uncharged, but they can lose their hydrogen to have the formula COO with a negative charge. In order to gain a proton, basic groups have to be in an acidic enough environment, and in order to lose a proton, acidic groups have to be in a basic enough environment. Now, the definition of what's acidic or basic enough is going to be based on how stable the group is when it's charged. For example, an acidic group that is relatively stable when charged is going to deprotonate more readily. The pH at which the ionizable group is charged is known as the pKa, which is defined as the pH where half of the ionizable group is charged and half is not. To illustrate this concept, I've drawn out an example titration curve for the amino acid glycine. Glycine has two ionizable groups, this basic amine group and this acidic carboxylic acid, and in fact, all amino acids have these two ionizable groups. The way these titration experiments work is you start out with glycine in an acidic solution, and then you gradually add base and measure the pH. So on the x-axis here, you have the amount of base that you've added, and then on the y-axis, you have the measured pH of the solution. At the start of the curve, the glycine is going to be in a very acidic environment, meaning there's lots of protons around. This means that both the basic amine group and the acidic carboxylic acid are going to be protonated. Overall, as you start adding in base, the pH is going to go up. However, there's going to be certain regions where the pH is going to go up more slowly than others. So in this first flat part of the curve, we're adding in base, but the pH isn't going up very much. And the reason is that this glycine, which is currently existing in a totally protonated state in the solution, is acting as a buffer. So as we add in base, we're getting more OH in the solution, but this carboxylic acid is giving up its hydrogen in order to buffer that extra base in the solution. So in this part of the curve, we're seeing this form of glycine transform into this form of glycine with that deprotonated carboxylic acid. Eventually, as we add in more base, all of the glycines in the solution will have a deprotonated carboxylic acid, at which point they can no longer buffer the solution. So we'll see the pH go up dramatically. At the middle part of this buffered flat part of the curve, that's where about half of the carboxylic acid is going to be in its uncharged form, and about half of it is going to be in its charged form. So that represents the pKa of the carboxylic acid, and that occurs at a pH of right about 2. Now, as we continue adding in more base, eventually we'll get to a point where the pH is so high that this amine group actually becomes deprotonated as well, causing it to lose its charge. So in the second flat part of the curve, we're seeing this form of the amino acid transform into this form of the amino acid, where both the amine group and the carboxylic acid are deprotonated. The loss of that amine group hydrogen buffers the solution as well with a pKa of right about 9. Eventually, all of the glycines are going to lose that proton on their amine group, and the pH is going to rise dramatically as it's no longer able to buffer the solution. Physiological pHs are generally between 2 and 9, so most of the amino acids in our body exist in this form where the amine group is protonated, but the carboxylic acid is not. The reason that this is important to consider for drug elimination is that charged ionized groups are going to be more aqueously soluble. And that means they're going to be more soluble in urine and more readily eliminated from the body. Recall that drug elimination is primarily done by the kidneys, which filter blood and create urine through a complex system of capillaries and tubules known as the nephron, which is shown here. As drug passes through the capillaries in the nephron, any drug that's in that blood has the opportunity to be absorbed into the tubules and eliminated through the ureter. If a drug gets into the tubules and the pH of that environment is such that the drug goes from being in an unionized form to an ionized form, it's going to be very unlikely to reabsorb back into the capillaries. On the other hand, a drug that is unionized in the tubules could reabsorb back into the bloodstream, making elimination less efficient. This means that altering the pH of the urine can actually make drug elimination more efficient, which can be really useful in the setting of medication overdose. So let's say you have a patient that overdosed on a medication that is a weak acid. Examples of medications that are weak acids are aspirin, phenobarbital, and methotrexate. The pH of blood is a pretty neutral pH, so some of this weak acid medication is going to exist in its protonated uncharged form in the blood. I've represented that here with the shorthand HA. In the nephron, some of that drug is going to move from the capillaries to the tubules. But if it remains protonated and uncharged, some of that is going to be able to move back into the capillaries and into the overall bloodstream. But if we make the pH in the urine a lot more basic, once the drug absorbs from the capillaries to the tubules, it's going to very efficiently lose that proton and become charged. And once it's charged, it's much harder for this form of the drug to make it across the membranes of the tubules and the capillaries in order to get back into the bloodstream. So effectively, it gets trapped in that alkaline environment. Now, how do we go about making the tubule a more basic environment? Well, we can actually just add a weak base like sodium bicarbonate to the blood. A major goal of the kidneys is to keep the blood at a safe range of pH. So the kidneys have a lot of mechanisms in place to actively transport this extra base into the urine. As long as the kidneys are functioning normally, they'll have no problem taking this extra base in the blood and moving it to the urine, making the urine more basic and allowing the weak acid drug to become trapped there. This concept is exactly the same for drugs that are weak bases, such as amphetamines. These drugs will become charged in more acidic environments by becoming protonated, which means that if we make the urine more acidic, the drug will get trapped in the tubules and eliminated more efficiently. We can make the urine more acidic by giving IV ammonium chloride and letting the kidneys do their job of deacidifying the blood by moving that excess hydrogen into the urine. Now, one thing that's important to be aware of is there's a class of drugs called tricyclic antidepressants, and these drugs are weak bases. Since these drugs are basic, theoretically, treating with IV ammonium chloride would increase elimination of the drugs in the urine. However, counterintuitively, overdose on this class of medications is actually treated with sodium bicarbonate and not ammonium chloride. The reason for this is that tricyclic antidepressants block sodium channels in the heart and cause arrhythmias, which can be fatal. And adding sodium to the bloodstream can help the sodium channels function more normally. In this situation, adding sodium to the blood is a higher priority than adding hydrogen ions for more efficient urine elimination. The main thing you should remember from this video is that drug elimination can be made more efficient by altering the urine pH. If a drug is a weak acid, meaning it gives up a proton to become charged at a pH above its pKa, making the urine more basic with sodium bicarbonate will trap the ionized drug in the urine and make elimination more efficient. If a drug is a weak base, meaning it accepts a proton to become charged at pHs below its pKa, making the urine more acidic with ammonium chloride will increase elimination efficiency.